Okay, good morning, everybody. Thank you for making it to the last 8:30 class of the course. So in the last lecture, we were talking about implementing generic types, right? Now remember, a generic type is a type that is parameterized over other types. So what that means is that you can create a type where the user is able to specify some other information about the types that your type is going to use. So the example we were looking at in the last class was this thing called pair. Right? A pair just represents two values. The two values might have any types that the user gets to specify. Right? So remember, when you're implementing a generic type, that's different than when you are using a generic type. So we've used lots of generic types in the course. You make a list, you say it's a list of string, right? And so when you use a generic type, the user is responsible for specifying what are the types that they want to use as part of their generic type. When you're implementing a generic type, you don't know what types the user wants to use, so you end up using these very short names for your type parameters, right? So our pair class says that T1 and T2 are the generic type parameters of a pair. Right? When the user makes a pair, they specify some specific type for T1 and they specify some specific type for T2. But inside your implementation, you just refer to T1 and T2 as your types. So our first field is has type T1, and our second field has type T2. They're both public, so the user of the pair class can access first and second directly by name. Right, and there's an example of a method that returns a pair made up of two integers. Right, and this just finds the maximum element in this list T, returning the maximum element and the index of the maximum element in the pair. Right? So the returned pair, the first element is the index, and the second element is the actual maximum value. Right? And so there's an example of a very simple generic type or generic class. Right? So now we've looked at other data structures. Well, we looked at stack and list, I guess. So we can go ahead and implement a generic stack class now. So I'm going to start by implementing a generic stack based on an array. Right? So remember, we had an array-based stack. So here, this used to be a stack of string, right? So that E used to be a string. Now we're going to make a generic stack, so a stack can hold elements of any one specific type. So when we create our class, right, we make it generic by putting in the angled brackets, and then we pick a name for our type parameter. Typically, if you have a collection, the type parameter is E or T. E is short for element. Right? And so we have a stack of some generic element type. Right? Now, you would like to do the following. Right? So if you're making an array-based stack, you would like to write, you have an array of type E elements. So that's what you want to write. Everything else stays the same. Right? Now, the problem is, as soon as you write this, so you can write this line here, that's fine. But as soon as you try to make a new array of type E, the compiler will flag that as an error. Right? So in our constructor, we have to initialize our field stack. Right? So we need to make an array. We need to make that array. As soon as you write new and then some generic type name in here, that causes a compilation error. Right? The compiler will tell you generic array creation is not allowed, which seems inconvenient. Right? So in Java, you're not allowed to create an array of generic type. This is probably an oversight in the language, but the oversight is caused by the fact that generics were introduced late into the language. Right? Arrays were in the very first version of the language. Generic types didn't come until version 5 or something. Right? And so there was this incompatibility between arrays with arrays and the way that Java decided to implement generic types. Okay, so now you think, well, maybe we're stuck. Maybe we can't implement the stack this way. But there is a way out. Right? So the solution is to make an array of object. Now, we talked about this briefly in the previous class. Right? So if you make an array of object, you can put anything you want into the array. Right? Because object is the superclass of all, or is NS is an ancestor class of all other types in Java, all other reference types in Java, right? But you can still do this. So let's take a look at what this looks like. Right? So instead of making our generic type E, an array of generic type E, we'll make an array of type big O object instead. Right? Now when we make our array in the constructor, there's no problem, right? The compiler will let you make an array of big O object, right? Because object's not a generic type. Right? Okay, now what you have to be careful about is the fact that arrays and generic types don't play nicely in Java. So arrays in Java are said to be covariant. Right? So this is a first time you've seen this term in this course. Right? So if you have a subtype of something, so if sub is a subtype of super, right, then what is true in Java is that the array of sub is also a subtype of an array of super. Right? So this is kind of interesting, right? Sub is the subclass of super. For arrays, an array of sub is also a subtype of an array of super, which is interesting, right? So if I have an array of object, right, then an array of string, you can consider that to be a subtype of array of object, right? So array of string is substitutable for an array of object, right? String is substitutable for object. We already know that. Right? But it's interesting that an array of string can be substitutable for an array of object. Right? So let's see what happens. Let's see what the consequence of this is. Right? So here's my array objs. Right? It's an array of big O object. Right? So can I make an array of integer and store a reference to that array in objs? Right? Well, you go back to the previous slide. Right? And this says that if sub is a subtype of super, then an array an array of sub is a subtype of an array of super. Right? So, is integer a subclass of object? The answer is yes. So, is an array of integer substitutable for an array of object? The answer is yes. So, does this compile? The answer is yes. It compiles. So that's fine, right? All right. Does that compile? Right? And so here we're taking the string hello and assigning that to the first element of objs, right? And now you ask yourself, well, does this compile, right? And so the way you solve this problem is you look at the type on the runtime type or the actual type of the object. So that's string. Now you look on the left-hand side and you ask, what is the declared type of that, right? Well, that's objs0 is an object reference, right? Or it's a variable that can hold an object reference. Right? So can I put a string into an object reference? The answer is yes. Surprisingly, this compiles. Right? And so this is one of the reasons why you can't make a generic array in Java. You run into all sorts of funny problems related to types and substitutability. Right? So this actually compiles, but does it run? And the answer is no. Right? So your compiler will happily accept this. When you run the program that contains this code, that's when it crashes. Right? So when you actually try to put the string into the array, right, or when you try to assign the string to a big O object that's part of this array, that's when it fails. Right? So now at runtime, you get a class cast exception, I think. Is that what you get? I can't remember what type of exception. You get some kind of exception when you try to store a string into an array of object. When you try to store a string into an array that's actually an array of integer, right? So now you have a problem, right? And so this does not run cleanly. Okay, so generics in Java are invariant, right? Arrays are covariant, generics are invariant, right? So if I have two distinct types, T1 and T2, right, and I have some generic class like list, right, then there's no relationship between a list of type T1 and a list of type T2, right? So there's no relationship whatsoever between these two, other than they're both lists, right? So there's no inheritance relationship, there's no association relationship, there's no dependency relationship, et cetera, et cetera, et cetera, right? There's no relationship at all between these two types. right? So the reason that the designers of the language decided to do this is to make sure that the generic types are type safe, right? Arrays, not type safe, right? Make an array of integer, store that in a reference that is an array of object, works fine, right? Assign a string to that array, compiler thinks that's fine, right? Even though it's actually an array of integer, right? Does it run cleanly? The answer is no, it doesn't run cleanly, right? You want to avoid this problem here, right? You would like to catch this error at compile time rather than having to run your program and finding out there's an error when you run your program, right? So for the generic types, this doesn't, does this compile, right? So we have a list of object here, right? You have an array list of integer here, right? Now we know that array list inherits from, we know that an array list is a list, right? So you would think that I'd be able to store an array list reference in a list reference, but this doesn't compile, right? Because an array list of integer is not substitutable for a list of object, right? So this doesn't even compile, which is the situation that you would prefer to be in, as opposed to the situation with arrays. All right, now back to our stat class, right? So all we have to, question, yeah?
Why would you rather the error be caught at compile time?
It's much easier to catch an error at compile time than having to compile your program, run it, and then catch the error at runtime. The problem is at runtime, you may not actually have written the code that causes the error, right? So you won't know there's a problem until someone tells you, hey, look, I did this, and now I ran my program and it barfed, right? And I traced it back to this issue here. Whereas if you can catch it at compile time, everybody knows that there's a problem right away. Yeah, so you always want to catch errors early as opposed to catching them late. Yeah. Okay, now back to push and pop. So push and pop are exactly the same as what we talked about earlier, right? The only difference is now when you push an element, right, you're pushing an element of some generic type E. Right? Your stack is a stack of big O, your array is an array of big O object now, instead of whatever it was before, string or integer. Right? So none of this changes except for that right there and that right there. Everything's exactly the same. Right? For pop, instead of returning an element of type string, we're now returning an element of type E, right? The generic type. The only thing that's annoying here is this line here, right? So when you get the element to remove from the stack, right, you have to go into the array and find the element, right? So that's at the top index, right, in the array this.stack. Right? Now remember, in our implementation, this.stack is an array of big O object, right? And so the element type here is big O object. The problem is the user needs an array, an element of type E. Right? So you have to cast the value that you get out of the array to type E so that you can return the correct, you can return a reference to an object of the correct type for the user. Right? So that's the only thing you have to remember here, right, is that you need this cast now. Right? That's an array of object. If you want to return an element of type E, you have to cast that element to type E. Otherwise, everything's exactly the same. None of the other code changes. Right? Oh, this is safe, by the way. Right? So if you write this line in Eclipse, Eclipse will underline this line and tell you that this might be an unsafe cast. Right? Because Eclipse doesn't know, all Eclipse knows is that this is an array of object. Right? It doesn't actually know that the element type is of type E. The programmer knows, though, it's of type E, because the only way you can add an element to the array is through push. Right? And push always takes an element of type E. Right. Okay, one more thing to do. We have to change our interface to be a generic interface now. Right? So there's our original interface, right? There's our stack interface, right? It's a stack of string in the original implementation, right? So its push method takes in a string, its pop method returns a string, right? It's trivial to turn this into a generic interface, right? Add your generic type variable inside the angled brackets up here. Change push so that its parameter is type E, change pop so that its return value is type E. There's your generic stack interface. Right? So it's usually trivial to convert a non-generic interface into a generic one. Right? Finally, one more thing we can do. Right? We take our generic array stack class, right, and now say that it implements our generic interface. Right? So there's our array stack class. It's generic. Right? It implements our generic interface now. Right? So it implements stack E. Right? In this particular case, it's important that these two names be the same. Right? We have a stack of some. Our interface is an interface for a stack of an element type E. Right? This E here has to match that E there. Right, and that's it. So it's normally very easy to convert a class that's not generic into one that is generic. Right? There's a few little things you have to watch out for, like if you have an array of object, if you have an array, you have to replace it with an array of object. But other than that, things are normally pretty straightforward. Right? All right. Any questions about converting the stack to a generic stack? All right, so more generic stuff. So this is lecture deck 28 now. So we're going to look at another data structure that we haven't looked at yet, and so there's something called a queue, which is closely related to a stack. Right, so that's an example of a queue, right? So this is a queue of people, right? In a polite queue, right, there is the notion of the front of the queue, so that's the person at the front, right? And there's a notion of the back of the queue. Right? If people are being polite, the first person out of the queue is the person at the front. Right? When you want to join the queue, you always join at the back. Right? So you don't butt into line in the middle somewhere. Right? If you want a queue where you can butt into line in the middle, you have something called a priority queue. Right? But we're not going to look at that. You'll look at that in CISC124, your data structures course. Right? So first person in line, first person to come out. Second person in line, second person to come out. Third person in line, third person to come out, and so on and so on and so forth. Right? So like a stack, queues, the traditional queue only supports two operations. NQ is the operation where you join the queue at the back, and DQ is the operation where you remove the first element from the queue. Right? Normally, it's an error to attempt to DQ an empty queue. Right? So NQ, add, DQ, remove. Right? If you're going to implement one of these in practice, you would add more operations. Right? It's useful to know how many elements are in the queue. Right? So you might provide a size method. It's useful to know, is the queue empty? So you might provide an isEmpty method. Some queues let you look at the first element without taking it out. So peek lets you get the front element, but it leaves the front element in the queue. You might want to search a queue for a particular element, so you could do contains. You can iterate over the elements of a queue. You can check if two queues are equal. You can you can generate the string representation of a queue, and so on and so on and so forth. Right? There's lots of operations that might be useful with a queue. But the important thing to remember is that you can only access the queue via the front. You can only access elements of the queue via the front element. Okay, so in a picture, this illustrates the operation of a queue, right? So in an empty queue, the front and back element are both they both point at nothing, right? There is no front or back element. When you NQ an element into the queue, right, the front and back element point at the same element, right? They point at the first element in the queue. When you NQ element into a non-empty list, right, you add the element to the back of the queue, right? And now your back element updates to reflect the fact that there's two elements in the queue. Right? NQ another element, right? It joins the queue at the back, right? Update your back reference so that it points at the new element, right? NQ another element, and then NQ a fifth element. Oops, sorry, where'd the arrow go? Is it here? There we go, right? When you DQ, right? So when you DQ, you're going to want to return the A back to the caller, right? So conceptually, right, if you're in a physical queue, everybody moves forward in the queue, right? So one more time, right? So DQ, right? So conceptually, Is this going to play? There we go. Right, conceptually, everybody moves forward. Right? Now, if you imagine that this thing here is an array, right, you don't want to implement it this way. Right? Because if I implement it this way, right, when I DQ, I have to shuffle, oops, sorry. When I DQ, I have to shuffle all of the remaining elements one position forward in the queue. Right? That makes the DQ operation become O n. Right? That makes it be in complexity big O of n. Right? Because I have to move n minus 1 elements forward in the queue. So conceptually, this is what happens. We're not going to implement it this way. Right? DQ the next element, right? The B gets returned to the caller, and again, conceptually, everybody moves forward in the queue. Right? I'm just going to click ahead so that, right? Last element, DQ it. It comes out, right? And there is no front and back element anymore. Okay, so queues are called FIFO data structures, first in, first out. Right? They're also called LILO data structures, last in, last out. Right? The first element included in the queue is always the first element that's accessed from the queue. Right? And these, like stacks, these show up widely in many computing science and computer engineering applications. Right? Many online services use some kind of queue. Right? So you have some sort of online customer queue. Right? Web servers use queues to service requests. Right? So millions of people are hitting up Amazon's website all the time. Right? Every time you click to go to Amazon or some other large website, right, the web server that's responding to your request, there's probably a bunch of other people in a queue waiting for their web page to load as well. Right. Your operating system uses queues to distribute most of the resources that a computer can provide. Right? So there's a printer queue. You might not know this if you've never been in an office situation, right? But if there's lots of people connected to one printer and everybody's trying to print something, right? Everybody goes into a queue, right? The first person's document gets printed, then the second person, then the third person, and so on and so on and so forth. Right? Internally, your CPU has a queue, or your operating system has a queue that provides programs on your computer that are running access to the CPU. Right, so at any given time on a modern computer, there's probably hundreds of programs running on your computer. Right, you've only got one CPU, so somehow the operating system has to provide each one of your programs access to the processor. Right, so all of the programs go into a queue. They all get serviced. They all get a little chunk of time on the CPU. And then they go back into the end of the queue. Right? There's a very famous algorithm called breadth-first search that searches a graph or a tree. It can be implemented using a queue. There's a whole branch of mathematics devoted to this. It's called queuing theory. Okay, so we're going to make a queue. We're going to make several different queue implementations, just like we did with a stack. So we're going to start off by making a generic queue because we know how to make generics. We know how to make generic types now. So we're going to make an interface called queue. Right? It holds elements of type E. Right? It's almost exactly the same as stack. Right? There's a size method. There's an isEmpty method. Right? Instead of push and pop, there is NQ and DQ. Right? Otherwise, they're exactly the same. Right? So NQ is more or less push. Right? DQ is more or less pop. Right? Front and back, these return the front and back elements of the queue. So those are a little different, but they're not difficult to implement. Okay, so if you wanted to use a list, it's trivial to implement a queue. Right? So it's almost exactly the same as a stack, except that DQ removes the element at the front of the list instead of removing the element at the back. Right? So remember in a stack, whenever you add an element to the stack, you add it to the end of the list. Right? Whenever you pop the element from the stack, you remove the last element of the list. Well, with a queue, we're still going to add at the end of the list, but we're going to remove from the front. Right? So we can make a list queue class. Right? It's generic. Right? right? It implements our generic queue interface, right? Internally, there's just a list of type E, right? And I'm going to call it Q, right? The constructor simply initializes Q so that it's in a list of some kind. So we're going to use an array list in this case. Right? Size simply returns the size of the list, so that's easy, right? That's just this Q.size. NQ adds an element to the back of the queue. In our implementation, we add the element to the back of the list, right? So this .q.add, add the element. Don't forget the Q here, right? Remember, you're adding to the list here. If you write this .add, or this .nq, you end up calling nq recursively, right? So be a little bit careful here, right? To dequeue, I'm going to check, is the queue empty? And if it's empty, I'm going to throw an exception, right? So instead of writing in the validation code here, I just created a little method here that does the validation for us, right? This is useful for first and last, right? So to remove an element from the queue, we remove the first element from the list, right? So remove the element at index 0, right? That's exactly what you don't want to do, right? Because when you remove an element from the front of the list, all of the other elements in the list have to shuffle forward one position, right? So your dequeue operation is now in big O of n, which we would like to avoid if we can, right? Front, you simply return the first element of the queue without removing it, or your first element of the list without removing it, right? So you use get. It's, if the queue is empty, you're going to throw an exception, right? That's why I created the method, because I don't want to repeat this code in dequeue front and back, right? I'm going to minimize code duplication by creating a method instead. Back simply returns a reference to the last element in the list. So you return the element at index q.size minus 1, right? And toString, well, the toString is easy to implement because we can just use the toString method that we got from the list. Right? So it's easy to implement this class, right? But the disadvantage here is that we have this big O of n dequeue method. All right, now we can fix the big O of n problem. We can make the always big O n dequeue become, on average, big O1 dequeue if we implement the queue ourselves using an array. Right, so this is similar to what we did with the stack, right? So with the stack, we started with a list, then we went to an array. So what does the array implementation look like? It's a little bit more complicated, right? Because the removal, dequeue and enqueue happen at the opposite ends of the queue, right? With push and pop, everything's happening at one end, right? So with the array, we could just add and remove from the end of the array, right? With the queue, there's things happening at both ends, so we have to be a little bit more clever in our implementation. So instead of just 2 fields, the array and top with a stack, we're going to have 4. What do we have? We had array, top, and size for stack. We're going to use 4. So we have our array to hold the elements. Right? Size is the number of elements in the queue. Right? Front is going to be the index of the element currently at the front of the queue. Right? And back is going to be the index of the element currently at the back of the queue. Right? If the queue is empty, it's not clear what front and back, what their values will be. Right? So front, index of the element at the front, right, of the queue, and back, index of the element at the back of the queue. All right, so when you start out with an empty queue, this is what we're going to, this is how we're going to initialize an empty queue. Right? So this is a new empty queue. Right? This is not every empty queue. Right? You'll see what I mean by this in just a second. So when we make a new empty queue, we have our array. Our array is initialized. When we initialize our array, all the elements are null. Right? We're going to have front point at index 0. Right? We're going to have back point at index minus 1. Right? So back is not a valid index in this case. To enqueue an element onto the queue, we're going to use an algorithm that's similar to pushing an element onto the top of the stack. Right? So if the array length, if the number of elements in the queue is equal to the capacity of the array, if array length equals, that was weird. All right. If the capacity of the array is equal to the number of elements in the queue, right, we have to resize the array. This is going to be a little bit tricky, so we have to wait for this. Right? We're going to move back one position to the right, and then we're going to set the element at array back to the n-queued element. Right? So we start out with this. Right? We're going to n-queue an element, so I'm going to add 1 to back so that it also points at 0, so its value is also 0. Right? And then I'm going to write into the element at index back. Right? So back goes up by 1, and then I write the A into ARR back. Right? I'm going to add another element. I'm going to enqueue another element. So add 1 to back, so it goes to 1, and then write into index 1. Right? And again, right? Add 1 to back, write into the element at that index. Right? And so after I enqueue 5 elements, we end up with the following array. Right? Okay, so what about dequeue? So to dequeue an element, right, I don't want to shuffle elements around, right? Because as soon as I start shuffling stuff around, that's going to end up producing big O of n complexity. So instead, what I'm going to do is we're going to remember the element that we want to return back to the caller. Right? So that's just the current front element. Right? So that's the element at array front. Right? I'm then going to remove the element from the array by nulling it out explicitly. Right? I'm then going to move front 1 position to the right, so I'm going to add 1 to front, and then I'm going to return the element. Right? So, oops, sorry. So in this situation here, right, I'm going to remember what the A is. Right? I'm then going to overwrite the A with null. I'm going to move front 1 position to the right. Right? So instead of moving the B, C, D, E forward 1 position in the array, I just move the index 1 position backwards in the array. Right? And we end up with that. Right? The A comes out, overwrite the A, front moves over 1 position to the right. Right? Do it again. Right? So remember the B, overwrite the B with null, move front 1 position to the right. Right? One more time. Right? Remember the C, erase the element here by overwriting it with null, move front 1 position to the right. Right? And if you do it again, so that there's only 1 more element in the queue, right? Front and back both point at the element E. If you do it again, right? Remember the E, overwrite the E with null, and then move front 1 position to the right. Right? And so now you end up in this situation here. Right? So now you end up with an empty queue. Right? And front and back are, the relative position in front and back look like that. Right? So back is 1 less than front. Right? Just like it was when we had an empty queue, a new empty queue. Right? So with a new empty queue, back was -1, front was 0. Right? So you might think that this is a possible way to determine whether or not a queue is empty. Right? But you would be wrong. So let's take a look at why we're wrong. So we're going to enqueue again. Right? So I enqueue the F. Right? And I keep on going. So I enqueue a bunch more elements. Right? Now eventually back ends up at the end here. Right? And so you would think, so what happens if you enqueue another element? Well, there's still 5 more places that I can use in this array. Right? So our array is not full. Right? So we can still enqueue more elements. Right? So when we enqueue another element in this situation, back wraps around to the front of the queue. Right? And so back, right? Remember, it's the element of the current back element. It's possible that back, the value of back is less than front, and the queue is not empty. Right? If you keep on going, right? Now the queue is full, right? Or now the array is full, right? Back is 1 less than front, right? Which shows you that you can end up in a situation where the value of back is 1 smaller than front, but the queue is not empty. In this case, in fact, it's full, right? So just looking at the relative values of back and front does not tell you anything about the size of the number of elements in the queue. Okay, so I'm now going to dequeue the queue, right? So to dequeue, we're going to remember the F, right? Overwrite the F, move front 1 to the right, right? I'm going to do that a bunch of times until I get to here, right? What happens if I dequeue again? Well, the P comes out, right? Front is now going to wrap around to the front of the queue, like that, right? So both front and back, they're going to wrap when they get to the last element of the array, right? And if you keep on going, and if you keep on going, of course, the queue will come out, front will move over, right, and so on and so on and so forth. So everything's always moving to the right. If they fall off the end of the array, they come back to the front, right? And so you can view this as what's called a circular array. So this picture here, right, is equivalent to this picture here. All I've done is I've taken this array and I've wrapped it around to be a circle, right? So there's front, right? There's back, right? Every time you NQ, back moves clockwise, right? Every time you DQ, front moves clockwise. So front and back are always moving clockwise on this thing, right? And so that's called a circular array. This is also itself, if you implement a queue this way, this becomes a circular queue, which is useful for some applications. The size is fixed, but in certain applications, that's okay. Right. Okay, so how do you implement this thing in Java? Well, it's pretty straightforward, right? It's almost exactly the same as a stack, right? So it's an array queue instead of array stack. It implements queue instead of stack. Right. Our array, again, it's just an array of object, right? Instead of top and size, we've got front, back, and size. Right. To make an new empty queue, right, you make an array of some default capacity, right? Whatever you want to pick, it doesn't matter, right? It's useful to make it bigger than 0, right? Set front to 0, right? Remember, that's the index of the current front element, right? Back, you can set to whatever you want. I'm going to set it to -1. Right? Size is 0, right? No elements in the queue. You can implement a copy constructor very straightforwardly, right? To make a copy constructor, I need to copy all the stuff out of the other queue, right? So I need to copy its array, right? The easiest way to copy its array is to use array's copy of, right? I need to copy its front and back values, and I need to copy its size, right? Copy constructor, straightforward. The front method, right? So I really should have created a method that validates, checks if the thing is empty, and if it is, it throws an exception, right? But I guess I didn't. So anyway, we'll go with it, right? So check if is the queue empty. If it is, throw an exception because there is no front element, right? Now, what's the front element? Well, it's just the element at this front, right? Remember that your array is an array of object, so I have to cast that to E so that I can return an element of type E. Right. For back, you just want to return the back element. So it's exactly the same as front, right? You just return the element at this back, cast it to E because you have an array of object and you need to return an element of type E. What about DQ? So DQ, now remember with DQ, you're going to adjust the front index, right? You have to take care of the case where the front index, when you move it to the right, falls off the end of the array, right? So step 1, remember what is the element that you want to return to the caller, right? So that's just the element at this dot front. Step 2, null out the element, right? So overwrite the element at this dot front with null. Right? Now I need to adjust front so that it's 1 larger. If it falls off the end of the array, I want it to wrap around to 0. Right? This is dead easy to implement. You add 1 to front. Right? You compute the remainder with the length of the, you divide by the length of the array and compute the remainder. Right? So if this front is the last index of the array, right? Then when you add 1, that becomes equal to the length of the array, right? When I divide that by the length of the array and compute the remainder, you get 0, right? So that automatically wraps the index for you. Decrease the size of the queue by 1 because we took something out of the queue, and then return the element. Don't forget to cast the element, that variable there, to type E, because you need to return an element of type E. Right? Okay, so what about enqueuing? Right? So enqueuing, we're going to play the same trick. Right? We're going to do something with back. We're going to add 1. We're going to compute the remainder after dividing by the length of the array. But there is a slight complication, because if you try to enqueue into a full queue, or sorry, into a queue where the array is already at its maximum, has the number of elements in the array is equal to the capacity of the array, you have to resize the array. It's slightly complicated because of the way this queue is working. Right? So imagine this is my queue. This is the state of my array for a queue. Right? It's full. Right? Front element is here. Back element is here. Right? I need to resize this array. Right? So the naive way to resize this array is to call arrays copy of. Right? And copy this array into an array that's double the capacity. Right? So there's my array that's double the capacity. If you use arrays copy of, it copies the queue, the element at index 0 into the element at index 0, the element of index 1 into the element of index, into the element at index 1, and so on and so on and so forth. Right? And so now your queue that looks like this in the new array, but notice back and front are all messed up. Right? My next free element is over here. Right? So back really ought to be over here somewhere. Sorry, back? Yeah, back should be over here, because the next element that I'm going to write into is here. Right? But back is way over here. Right? So the elements are now out of order in the new array. So you need to reorder the elements in the new array. Right? Or alternatively, when you copy the elements into the new array, do it in a more intelligent way. Right? So one way to do this is to start at the front element of the old array, right? And copy that element into index 0 of the new array, right? Then take the second element of the queue, right? And copy that into the second element of the array, right? Take the third element of the queue and copy that into the third element of the array, right? So in other words, I want to unwind that circular array so that it becomes that array right there. Right? So starting at the front element, copy these elements to the front of this array, right? Then wrap around, copy the remaining elements into the array, right? Like that, right? So that's the logic that we have to implement. It's pretty straightforward to do. You just need a loop, right? All right, so if the size of the queue is equal to the length of the array, we have a full queue, right? I have to resize the array. So now, instead of using arrays copy of, I have to do this manually. Right? So make a new array that's twice the capacity of the old array. Right? Now copy the elements from the old array into the new array, starting at this dot front. Right? So starting at this index, right, I want to copy into index 0 of the new array. Right? So that's index 0 of the new array. I want to start at the front index of the current array. Right? Each time through the loop, I want to add I to both of these indexes. Right? So on the second iteration of the loop, I is 1, so I want to copy into the second element of temp. Right? The element from the current array that's at front plus 1. Right? Now you have to remember that the index could fall off the end. Right? So if I keep on adding 1 to front, I eventually hit 15. Right? When I add 1 more to front, I don't want to use 16, I want to use 0. Right? But you can play the same trick again. Right? Add I, compute the remainder after dividing by the length of the array. Right? And that takes care of the wrapping for you. Right? This remainder operator turns out to be really useful in a lot of fundamental algorithms. So that, if you run that loop n times, that copies all of the elements out from the old array into the new array. Right? Now everything else is the same as before. Right? Reassign this array so that it points at temp. Right? Adjust front, right? Because front is now, front is now 0, right? Back is now the size of the q minus 1. Right? So front becomes 0, back becomes size of the q minus 1. Go ahead and add the element to the back of the array now. Right. Okay, what time do we have here? All right, this is going to be, I guess, the last substantive slide for this course. So this is going to be the, I'm going to update on Q to indicate that the remaining slides aren't part of the course. All right, so back when we implemented the copy constructor, right? Remember, the copy constructor for array Q, we passed in another array Q, right? But our array Q implements the Q interface, right? So for a copy constructor, it might be nice if array Q could copy any kind of Q, right? Not just an array Q, right? So it might be nice to provide a copy constructor, right? Or a second copy constructor that's capable of copying any object that implements the Q interface, right? Not just one that happens to be an array Q, right? Now the challenge with implementing this method is that you don't know how this other Q has been implemented. Right? You don't know if it's a list that's in this other Q. You don't know if it's a linked sequence of nodes in the other Q. You don't know if it's an array. You don't know if it's something else. Right? So when you try to implement this constructor, the only thing that you can use are the methods from the Q. Right? When you copy another Q, you do not want to destroy the other Q. Right? You don't want to modify the other Q. Right? You want to make an exact copy of it without changing or without permanently changing the other Q. So that's the challenge in implementing this method. Right? Consider implementing equals. Right? So you could override equals so that an array Q is possibly equal to another array Q. Right? But it's probably a lot more convenient to implement equals so that an array Q can be equal to any Q. Right? As long as it has the same number of elements and the elements are in the same order, they should be equal. Right? Again, the challenge you're going to have here is that you can only use the methods of Q. Right? You don't know how that particular Q that you're comparing to is being implemented. Right? And again, when you call equals, you don't want to permanently change either Q. Right? And so that's the challenge with implementing equals here for this particular question. Right? So I will leave those as exercises for the student to consider. Right? And I think that's it for the course for this year. So on Monday, I'm going to try very hard to get back your quiz. I'm pretty sure I'll get back. So I'll return your quiz, we'll take up the quiz, talk about the exam. Right? Other than that, I think we're done for the year. So the exam will only cover up to lecture 20, sorry, let me make sure I get this right. Lecture 28, sorry, lecture 28. 28. Right? Any questions before we wrap things up for the year? All right, super. If you want your quiz, come by on Monday. Otherwise, drop by my office sometime and pick it up after Monday.